I think he came back from his mother, somebody in his family came back to take care of him. I think that's how he ended up back in Bath County. I think did he get his undergraduate from UVA or then went to Yale, maybe? Something like that. Canada. So we're going to continue on chapter 11, section 2. We've got 2 more examples to do. So what we were doing in the second section, we were looking at probability for situations where we have a converse or a complement situation where you're asking the question, what's the probability of not doing something versus probability of doing something, whether it's to directly answer the question or whether it's to answer the complement by taking 1 minus the probability of not doing something is equal to the probability of doing something. And the second one was or statements. What's the probability of doing something or something else? And we used this additive property for addition rule for probability that said the probability of event A or event B occurring is equal to the probability of event A plus the probability of event B minus the probability of event A and B happening. So we looked at some card examples for that. I don't think we looked at these diagrams. Most of you had class last semester, but when we were talking about set theory, we said that we talked about intersections and unions, and the intersection of 2 sets in a Venn diagram is this overlap between the 2 circles. And so elements that are in both sets they belong to set A and set B. We would normally place them inside this overlap region. And then we had the elements in set A would be inside this circle, and the elements in set B would be inside this circle. And when you do the elements in set A or B, you just list all the ones that are in A or B. And you don't want to double count the ones that are in A and the ones that are in B, so you have to subtract out that commonality. So the same thing applies for probability. It's the same equation for probability. So the probability of event A or event B happening is equal to the probability of A plus the probability of B minus the probability of A and B. Now, if the 2 events are mutually exclusive, that means that there's no commonality between the 2. Then you just add the probabilities of each one. Now, the reason you never end up with a probability of greater than 1 is because these are all based on using the sample space as the denominator. So you're not going to compare probabilities for completely different, you're not going to say, what's the probability of flipping a coin and getting ahead, or somebody in this class name beginning with letter. Those are completely off. Those are different sample spaces. So we don't ever end up with a probability of greater than 1 by or, because you can't have a probability greater than 1. You can't be more certain than certain, completely certain, right? So, okay, so let's look at 2 more examples. So suppose we want to form 3-digit numbers using the set of digits 0, 1, 2, 3, 4, and 5. And we're going to answer 3 questions relating to it says how many numbers, and then we're going to answer a probability question. So we're going to do the counting first, and then once we do the counting, then we can answer the probability question. So how many 3-digit numbers are there possible? So to answer that question, we use the fundamental counting principle, which it says that if you have a multi-step process, then you count how many choices you have at each step. And as long as the choices in the previous step don't influence the next step, you can use the fundamental counting principle. So the question is, if we have a 3-digit number, how many of these numbers can we choose from? What about 0? Can you use 0? Yeah. So if you put a 0 in the first place, it's not a 3-digit number. So you really only have 5 digits. So you have 1 through 5. And then the next one, you can use 0 through 6, so there's 6 of those. And you can use 0 through 6, so there's 6 of those. And if you multiply that together, you'll get how many 3-digit numbers you can create using those numbers. We did this with, if we have just any 3-digit numbers, the total is going to be 900 because you have 9 times 10 times 10. But in this case, it's not quite that many. So it's 5 times 6 times 6. So it's 180. So they're only... well, you can finish it. Okay. So you have 180 numbers. So that's the total sample space. That's our denominator for calculating probability. Then the question of how many of these numbers are multiples of 5. So you do the same question. How many choices do I have for each number? Again, I have 5 choices for the first number because I can't have 0. I have 6. So this can be from 1 to 5. This can be from 0 to 6. Yeah, why did I put 6 in there? I don't know why I did that. Let me fix that. So 0 to 5, which is 6. 0 to 5. So you can go 0 to 5, which is 6 numbers. And what are the 2 choices for the last number to be a multiple of 5? 0 and 5. So that's the 2 numbers are 0 and 5. So I'll put 0, comma 5, which is 2 choices. So you multiply those together and you get 60. So now we're going to answer a probability question. If one 3-digit number is chosen at random from all those that can be made from the above set of digits, find the probability that the one chosen is not a multiple of 5. So to answer the question not being a multiple of 5, we haven't answered the question how many are not a multiple of 5, but we have answered the question what's the probability of them being a multiple of 5. So let's answer the not question, but the affirmative question. So the probability of being a multiple of 5 is the total number of numbers, 3-digit numbers made up of these 6 values, divided by the total sample space, which is 180. So if I were to pick a number, if I were to randomly choose a number out of this sample space, the probability that it would be a multiple of 5 is 1/3. So the probability that it's not a multiple of 5 is going to be equal to 1 minus 1/3. So I'm doing it in terms of probability and not in terms of the numbers. And the answer is 2/3. So it's the probability of 1/3 that it's a multiple of 5, therefore it's a probability of 2/3 that it's not a multiple of 5. It either has to be multiple of 5 or not a multiple of 5. So if you add these 2 probabilities, you get 1, which is certain. It's certain that if you pick a number out of there, it's going to be a number. That's kind of what 100% certainty means. Pardon me? Yeah, right. Okay, so this is kind of similar kind of thing. What is the probability that of 3 people selected at random, at least 2 were born on the same day of the week? So this is an at least thing. So you have to think about remember what we said is at least you can write it as an inequality. So what is the inequality that represents at least 2? That means 2, or you could say 2 or 3, right? Has to be 2 people or 3 people have the same day of the week. So it's great. X is greater than or equal to 2. So the opposite of that is X is equal to 1. But that doesn't make any sense because that would be the complement of at least 2 would be none. So no people. So what we need to do is figure out what the probability that nobody has the same birthday, and then you can take 1 minus that to answer the question that at least 2 people have the same birthday, or you could have all 3 people have the same birthday. So again, it's a fundamental counting principle. Basically, you have 3 people, and they're going to tell you what days of the week they're born on. So it's 3 parts to it. So here's the first person. So there's no restriction on what day of the week the first person is born to have them not have the same birthday. So there are 7 days of the week that the first person that he can be born on. Then the second person, let's say this person is born on a Saturday, just as one example. So he's born on a Saturday. That means that the second person, so that they don't have the same birthday, they can be any other day other than Saturday. So we could say any day except Saturday. That's what you would need to have so that they don't have the same birthday. So there are 6 choices for the second person, 6 days of the week that would make them different than the first person's choice. So let's say any day is Saturday, so let's say it's Friday. So this guy has a birthday on Friday, so the third person chosen would be any day except Saturday or Friday. So then that means there's only 5 days left of the week that this third person can have as a birthday. So you multiply those together and you get 210. So there are 210 ways that 3 people can have a different birthday. This is actually the numerator. The total number of possibilities, the total number of arrangements, which is the denominator, would be 7 times 7 times 7 without any restrictions, because the first person can have the birthday on any day of the week, the second person can have any day of the week, and the third person can have any day of the week. So that gives us a total of 7 cubed, which is 343. So again, the probability of not having the same day of birth is going to be equal to the number of arrangements where the people don't have the same day of birth divided by the total number of possible arrangements. And I don't know if we can simplify this thing down or not. I don't think so. Let's just put it in decimal form. So we're going to make it as decimal probability, which is 0.612. So the probability of having at least 2 having the same, at least 2 having the same day of birth is going to be equal to 1 minus 0.612, which is 0.388. So that's the answer. Again, that's using the additive principle. Well, it's using the complement principle of probability. You know, the long way of doing this is you could you could take a spreadsheet and you could write out all 343 possibilities, and then you could just scan through and mark the ones out that have, or put a check mark when you see 2 people having the same birthday of the week. That would take a long time because there are what do we say? There's 133. If you take the difference between, there's 133 different cases where that is. It's a lot easier to do it the way we did it, using the fundamental counting principle. And what the heck did they call this? I always forget. It's called the probability of a complement, which is kind of funny. That's my political comment for the day. The probability of a complement. It depends upon if you are Vladimir Putin or not, and you're Donald Trump. The high probability of a compliment about a different kind of compliment, of course. Okay, so I think I already assigned that, but if I didn't, did I assign that already? Yeah. So the next section is going to be about what's called conditional probability. Up to this point, for example, this particular example, the number of choices that I had, both the denominator and the numerator, was independent of what choice I made before. So there were 7 choices, and there were 6 choices in the second part of the process, but the number didn't change. If I chose Friday instead, if this person's birthday was he was born on a Friday, you'd still have 6 choices in the second case. Now, the conditional probability is related. There is actually an effect. The choice you make the first time is going to affect the probability of what happens in subsequent steps. So that's what we're going to talk about. Yeah. Yeah, I think I'm doing everything YouTube now. So there's too many people that have problems with the jar files or the. Yeah, you can't. Yeah, you can. So conditional probability are events involving an and. So we've done not, we've done or. This is and. So, conditional probability. The probability of event B computed on the assumption that event A has happened is called conditional probability of B given A. And we use this terminology. So it's we use P for probability. And before we've just had a letter representing the favorable event that we're trying to find the probability of. In this case, we have 2 favorable events, A and B, but the probability of B happening could depend upon what happens when you choose A. Okay, you'll see what that means in a minute. But that's how we use it. It's just a vertical line. It's not an L. Anything like that. And the way you calculate conditional probability is using this formula. So it says the probability of event B occurring given that event A has occurred is equal to the probability that A and B will occur divided by the probability that A has occurred. So this is the symbol for intersection, but in terms of what we're in this particular semester, we can just use the word and. So the probability that B will occur given that A has occurred is equal to the probability that both A and B will happen divided by the probability that A has happened. Now we actually don't use this definition that much. We rearrange the numbers or the terms. because what we're typically wanting to figure out is what is the probability of A and B happening given that we know or we can determine this and that. So let me just write that out. I can't remember whether I wrote it on the next page. So I'll just say typically we solve for the probability of A and B happening. So we get that the probability of A and B happening is equal to the probability of A happening times the probability of B happening given that A has happened. So that's the formula that we're going to use a lot. And that's what I have written there, so I wasn't sure if I had that next, so I'm just going to delete that. So it says demonstrate. So yeah, I'm not sure if I remember how to do that right now. We'll come back to that if I remember what I'm supposed to do. Okay, now just like we had mutually exclusive probabilities in the previous section, we also have this idea of two events being independent of each other. So if two events are independent events, it says if the knowledge of the occurrence of one of them has no effect on the probability of the other one. And that's what we've actually been dealing with a lot of our cases of like flipping a coin. So if we flip a coin, the probability of getting a heads or tails is 0.5. If we flip the coin again, the probability of B, that's event B, is flipping the coin the second time. The probability of that occurring is the same whether we got a heads or tails on the first flip. So that's an example of independent events. But if you think about cards, if you pick out a card out of a deck and you don't put it back, then the probability of picking that card again is 0 because it's not in the deck anymore. So that is the case where those would not be independent events. If you picked a second card, there's no way that you can pick the card that you've already pulled out of the deck. Now, if they're mutually independent, if they're independent events, then the probability of B happening given that A happens is just the probability of B happening by itself. There's no connection between the two. Or the other way around, the probability of event A happening given that B has happened is just the probability of A happening. Again, think of a coin, rolling a dice. Those are examples of independent events. But if you were to pick somebody out of this group to be president of the class, then the probability of picking that person again is 0, and the probability of picking somebody else for the next office is going to be greater because there's going to be less people to choose from. So that would be a case where they're not independent. So it usually is where you choose something out of a group of things and you don't replace the thing that you've chosen from. That's usually where they are dependent upon each other. So here is the multiplication rule of probability. Well, actually, I already wrote this down. So this is what it's officially called. The multiplication rule of probability, all we're doing is using the definition of the conditional probability formula, and we're just solving for the and part of it. And so you've already written this down. So if there are any two events, the probability of event A happening and event B happening is equal to the probability of event A happening times the probability of event B happening given that A has happened. If two events are independent, then it's just the probability of each event separately. So I just said this verbally. Let me just write it down. So flipping a coin twice. So if I said, what's the probability of getting heads on the first flip and a heads on the second flip? So it's an and question here. So event A is the first flip, and event B is the second flip. So the probability of getting a heads on the first flip is equal to 0.5, because there's two choices. There's heads or tails. The probability of getting a heads on the second flip is also equal to 0.5, because it's the same coin. So then these are the individual probabilities. In this case, they're independent events, so the probability of event B happening given that event A happening is the same as if it didn't, that's independent. So we use this formula. And so to answer the original question, you just multiply the probability of event A happening by the probability of event B happening, which is, you get 0.25. So it's a 0.25 probability that if you flip a coin the first time you get heads and you flip a coin the second time and get a heads, that's 0.25 probability. So that's the other options. You can get a head the first time, tails the second. You can get a tails the first time and a heads the second. You can get a tails the first time and the second time. Those are the four possibilities, and each of them have a 0.25 probability. And you get those just by multiplying the probability of each step. Here's another example, shooting free throws. So now, theoretically, I guess if you make the first one, you might get nervous and you might have a lower three for a percentage the second when you shoot two shots, or you may get more confident, you may make the second one. So, we're assuming that this person's ability at shooting free throws is independent of whether they made the first shot or not. It's completely random. Pardon me? Independent of every single important external stimulus. Yeah. Can you actually generate probability on anything usefully? Oh, without an external stimulus? Well, yeah, I mean, you just have to, yeah. Yeah, because I'd like to shoot free throws because I'm good at it, and it's very psychological, the whole process of shooting free throws. The question is, what I do is I always go by tens because that seems not as intimidating. So if I want to shoot 50 free throws, instead of counting how many I get out of 50, because then get to 20, 25 in a row or something, that seems, oh man, I'm bound to miss the next shot, so then you get tight. So I always think of it as 10, because shooting 10 free throws in a row is not that hard. And then I start all over again, and I'll say, well, okay, now I'm just shooting 10 free throws again, instead of trying to shoot 50 at one time. It's a psychological thing. Whether it actually makes any difference or not, I don't know. It's did I ever tell you how many free throws I've made in a row? My record? Yeah. So and it's kind of a funny story because being tall and playing basketball in high school, I didn't start playing. I tried out in 9th grade. I didn't make the team. My family's from England, so basketball is not some kind of family tradition. So I was never encouraged to play basketball. But then you're tall, and you're like, oh, you're tall, so you ought to play basketball. So the guy next to me in Ohio had a basket, so I would go over there and practice. And so anyway, I thought, hey, I'm getting better at this. Anyway, I played, but I was very uncoordinated. So I don't know if anybody's played basketball. You get those people that just, one of my nicknames in basketball was Hands, which meant I'd throw the ball and I'd I'm gonna, get nervous or whatever. So as a consequence, when you have a shortcoming, you can either give up or you can work really hard trying to overcome it. So I tried to overcome the whole not having great coordination by working on my dribbling and also shooting free throws. So I worked really hard at shooting free throws. And anyway, so here's and this is, you have to believe me, there's no official record on it, but it was in college, and I would go during lunchtime, and I would just, and it was usually not many people were there at lunchtime because they're going to class. So, the gym's empty. If you go at night, you never get a chance. So I'm shooting my three, so I would just shoot them in a row, get the ball, go back to the free throw line. So it was all me retrieving the ball instead of somebody throwing it to me. Anyway, my record is about 60. I don't remember the exact number, but what was that? Is that what you thought? You could never do it. So well, actually, that's a good point, because there's someone in my calculus class who plays basketball, and I thought, okay, I want to challenge them in basketball. It's Elena. So I said, I'm going to challenge Elena in free throws. So I need to go practice. And so the first day I did it, I probably shot about 75%, which is and then I would get better, and I got up to about 85, 90%. So 20 out of 25, that's 80%. And but getting above that, it's like playing golf. Anybody here play golf? You get to a point where you start to overthink things. You analyze your swing too much. Well, I was trying to get that extra little bit, and then I went, because I was trying to, okay, I'm going to do this, I'm going to do that, and then you don't have any rhythm to it. Yeah, so you have to you just have to accept where you are and go from there. It still is not as good as I'd like it to be, because I do have high standards when it comes to free throw shooting. Okay, anyway, so this is a person that has a 80%, on average, 80% free throw. It's an experimental probability. So the probability of him missing his free throw is 20%, or 0.2. So the question is, what's the probability of the four combinations here? So we're going to probability of making the first and missing the second, the probability of making the first and making the second, probability of missing the first, missing the second, and the probability of missing the first and making the second. So the way you do it, all you have to do is take the probabilities of each one of those events and just multiply them together, because I'm assuming that they are independent events. So in this case, the probability of making a free throw is 0.8. So that's the first shot. That's event A. Event B is missing the second shot. So the probability of missing the second one is 0.2. So you multiply those together and you get 0.16. So 16% of the time you're going to make the first and miss the second. Now, to make the first and make the second, the probability of making the first is 0.8. The probability of making the second is 0.8. So the probability is 0.64. So 64% of the time, this guy's going to make both free throws. The probability of missing the first, well, the probability of missing is 0.2. The probability of missing the second is 0.2. So the probability of him missing both is 0.04, which is pretty small. And then you have missing the first, making the second. You multiply those together, you get 0.16. So those are the probabilities of making and missing, all the four different combinations. And because it's not 50-50 anymore, it's not like flipping a coin, it doesn't end up being 0.25 for each one. If you add all those numbers together, if you take 0.16 plus 0.64 plus 0.16 plus 0.04, you'll get 1. Because the probability of doing at least one of these is 100%, because they're the only choices. So that's how you handle independent events. That's kind of an interesting thing. You know, you don't think about that. You know somebody's free throw percentage, but if somebody were to go randomly, you'd walk me over there, and I'm shooting 80%, and you know, if I only shot 2 free throws, the probability is that 64% of the time I'd make two of them. 16% of the time I'd make the first and miss the second. 16% of the time I'd miss the first and whatever the opposite was. I already forgot what it says. And there would be only a 4% chance that I would actually miss both of them, which is pretty small. I mean, that's a little, only 4% of the time. Okay. Now, let's look at a case. This is, and I'm actually going to skip that one. I'm going to do the second one first. So here's here's the one about puppies. So this is an example of a cute math problem. Okay, suppose 2 puppies are selected. It says as before. What was before? It says we had 2 people, Rebecca and Aaron, and they select a puppy at random. In this case, they're not replacing them. So once the puppy is taken by the first person, that puppy is no longer available, or that type of puppy is not available. So in this case, this is a case of conditional probability, because the first choice does affect the probability of the second choice. So what we're going to do is the probability of event A, that's basically the probability, and let's have Aaron go. So there's 2 people. We'll let Rebecca go first, because we're being polite here, being chauvinistic. Yeah, that's kind of, is that how they spelled it? And Aaron, how do they space? That's another one you could spell different ways. Okay, Aaron. So Rebecca's going to choose it first, and then Aaron. I'll say and then Aaron. Okay, so the probability of event A is probability of Rebecca choosing appointed, meaning the one that we're going to calculate the probability on, puppy. And the probability of B, given that A happens, is the probability of Aaron choosing the appointed puppy given Rebecca's choice. Yeah, say hi to Mr. Sass. Okay, so those are the 2 probabilities. So let's look at the different cases. So there are 4 different cases. So we're going to do case A first. So the first, so the probability of A in this case is the probability that Rebecca chooses a poodle. So the probability that Rebecca will pick a poodle is based on the information that's given in the problem. So there's 4 poodles, 2 terriers, and 1 retriever. So how many puppies do we have in our sample space? How many puppies do we have to choose from? 7. So our denominator is 7. How many poodles do we have? 4. So if you randomly pick a dog, which of course nobody really does, but is going to be 4 divided by 7. So that's the probability of Rebecca choosing a poodle. I've got to plug my headphone in. It just dinged on me. Hopefully I have it in here. Yeah, there you go. I'm a strong believer in that you always should have something you're doing to challenge yourself, whether it's shooting free throws. That's not very exciting, but so my latest, I can't run a marathon because my knees just wouldn't take it. So you got to choose something that you just. So my latest thing is I am going to try to. I've got my trumpet out. I'm going to. I haven't played trumpet since 10th grade, so I'm going to. There's a brass group locally that needs a trumpet player, so I'm going to do that. Anybody in here played an instrument? Trumpet? You played the euphonium. Well, they've got a lot of bass. They've already got enough. They've got too much of the low end. They've got lots of trombones. It's the what? Oh yeah, no, bass is in. They have the lower. They have 3 trombones, a couple of French horns, 1 trumpet player. You need more trumpet players. So. Huh? Oh, you get rid of one of them. Okay, I got it. Okay, is that a band joke? I didn't know that. Okay, so so the probability of event B happening, given that event A has happened. So what he's doing here is Aaron is going to pick a poodle, but what's changed is there is 1 less poodle, and there's 1 less dog. So in this case, because we're not replacing the poodle, there's 3 poodles left after Rebecca has chosen her poodle, and there are only 6 dogs to choose from. So the probability change, this probability changed based on what happened for the first choice. So the probability of event A happening, which is Rebecca picking a poodle, and Aaron picking a poodle, is going to be equal to the probability of Rebecca picking a poodle times the probability of Aaron picking a poodle, given that Rebecca has picked a poodle. So we take 4/7 times 3/6, which would be 12 40-seconds, which would be, you can divide by 4, so that would be, no, 3. So you get 4 over, what's that, divided by 3. Pardon me? Oh, 6? Yeah, you're right. You can divide by 6. Let's do that. So you get 2/7. So the probability, this combined probability of event A happening and event B happening is we multiply those 2 probabilities together. Okay, so that's kind of how it works. So let's do another one here. Rebecca picks a retriever. So let's remember there's 4 poodles. So I'll have to keep going back 1 page. There's 4 poodles, 2 terriers, and 1 retriever. 2 terriers, 1 retriever. Okay, so that's my dog selection. So to do the second one, what's the probability of Rebecca picking a retriever? So what did we do? We looked how many poodles we had divided by the total number of dogs. So how many retrievers do we have? 1. How many dogs do we have? We're starting over again, so 7. The probability of Aaron picking a terrier, given that Rebecca has picked a retriever. So now that I've taken one of the terriers, there's 4 poodles, 1 terrier, 1 retriever. Actually, a retriever. So sorry, there are now 4 poodles and 2 retrievers. The retriever has now been chosen. So Aaron how many terriers does he have to choose from? He still has 2. So that this choice, choosing a retriever, didn't affect the number of terriers available, but it does affect the total number of dogs available. So this becomes 6 still, because we only have 6 dogs to choose from instead of 7 dogs. So the second case, the probability of Rebecca picking a retriever and Aaron selecting a terrier is equal to the probability of Rebecca picking a retriever multiplied by the probability of Aaron picking a terrier, given that Rebecca has picked a retriever. So we get 2 divided by 42, which is 1/21. So let me see if you guys can do, so you guys online, this is to see whether you're awake or not. See if you can figure out what the next one would be. So just give me your final answer. So we'll see if they're paying attention or not. Let's see if they would put an answer in. Okay, who do we have here? We have Taylor and Josh, so I'm waiting for you guys for a response. What do you think, Tucker? What's the final answer? Okay, so I'm going to ask you the questions here to answer it. So Rebecca selects a terrier. So we're starting back with 7 dogs. How many terriers are there to start with? 2. And how many dogs? 7. Okay. Now, once one of the terriers is chosen, we have 4 poodles, 1 terrier, and 1 retriever. So Aaron selects a retriever. So how many retrievers do we have to choose from? 1. Yeah. So picking the terrier didn't affect the number of retrievers, and the number of dogs to choose from are 6 or 7. Because I've taken one of the terriers, so there's only I had started with 7 dogs, so there's now only 6 dogs left. So if you multiply these two together, you get the same answer as the previous problem. It's just they get flipped around. You still get 2/42, which is 1/21. And part of the reason is because the choice here doesn't affect the second choice as far as the number. If I chose here they're saying a retrieve. What's the chance? Well, let's do D, and then we'll come back and redo C. So what's the probability of Aaron picking, or Rebecca picking a retriever, and then Aaron picking a retriever? Yeah, 0, right? Yeah, because by 0, it would be 0/6, but it's still 0. Yeah. So in this case, the probability of Rebecca picking a retriever is 1/7. There's 1 retriever, 7 dogs. In the second case, there's 0 retrievers left out of 6 dogs. So you multiply those together and get 0. I mean, there's only 1 retriever, so the probability of magically creating a retriever is 0. And, you know, the same kind of thing applies here. If Rebecca picked a terrier and Aaron picked a terrier, it's kind of like the original problem where we had a poodle. The only difference is that this would be 2/7 and this would be 1/6. So when you don't have replacement, the denominator always decreases by 1 every time you make a choice. Now the numerator can decrease. It can be different because it's a different choice, different kind of dog, or it could decrease because you're choosing the same dog in both cases. So that's where you have without replacement. You can also do the same thing with replacement. In that case, it's the same kind of deal, except the denominator doesn't change, and also the numerator might change as well. So let's just think about it. So if we replace, say Rebecca gets a poodle, I don't know where they get the extra poodle from, but maybe before Aaron gets there, they go, hey, we need another poodle, bring it in. So we keep replenish the poodle supply. So in the case of Rebecca, when she chooses the first dog, it's exactly the same as our previous case. So you would have, we have 4 poodles out of 7. So that's the probability that Rebecca picks a poodle. The second choice, the probability that Aaron picks a poodle, given that Rebecca picked a poodle, well, it doesn't matter anymore because we're replacing the poodle. So it's still 4 out of 7 instead of 3 out of 6. When we didn't have replacement, it was 3 divided by 6. When we have replacement, it's 4 out of 7, so you get 16 over 42 is the probability. You're not bringing them in? No. Well, that's probably too much trouble. So the next one is Rebecca selects a retriever. So there's 1 retriever out of 7 dogs. So that's first probability. Again, if you replace the retriever, what that's going to do is it's not going to get any more terriers, so it doesn't affect the numerator choice that we have, but it does affect the denominator because we're back to 7 dogs again. So Aaron selects a terrier. There are 2 terriers out of 7 dogs. Again, in contrast, let's go back to this one. We had we had 1/7 as our first choice. We had 2/6 as our second choice. In this case, we have 2/7. So the probability is 2 over 49 for event A to happen and event B to happen. The third one would be Rebecca selecting a terrier. So there are 2 terriers out of 7. And again, we replace the terriers so that instead of only having 1 terrier to choose from, we have 2 terriers. And we have 7 dogs. So you get 4 out of 49 probability. In the case of the retriever, before we had the second choice, we didn't have any retrievers left, but now we do. So the probability of picking a retriever is the same, whether it's Rebecca or Aaron, because they still have the same total number of choices and the same sub-choices. So this one ends up being 1 out of 49. So that's how you calculate, use conditional probability in multi-step events. And the key thing is whether you're replacing something or not replacing something. I typically put a problem like this on the test, so make sure you understand what I'm doing. I think there's another problem in the book that's like this for homework, but you could also do it with cards. I think I wanted to see if there's a card problem here. Yep. So a card problem says, let 2 cards be dealt successively without replacement from a standard 52 card deck. Find the probabilities of each event. So what's the probability of getting a spade first, and what's the probability of getting a spade second, given that you got a spade first? So these are actually, you could think of this problem as what's the probability of getting a spade, and then once you get a spade, what's the probability of getting another spade? Or you could just answer the question, what's the probability of getting a spade if you get a spade first? Okay. We'll answer the second question there. So this is the actual, this is conditional probability. We're asking what's the probability of event B happening given that event A has happened. So there are 13 spades. So to start with, the probability of picking a spade would be 13 out of 52. Because we have 13 spades, we have 52 cards. When you take, if the first card is a spade, then there are only 12 spades left for the second pick. And there are 51 cards remaining. So that's the probability of event B happening given that event A has happened. If we wanted to know what's the probability of A and B happening, meaning getting two spades in a row, you would take 13 over 52, which is the probability of picking a spade the first time, multiplied by the probability of picking a spade the second time, given that you picked a spade the first time. And that's going to be a big number. I think you can simplify it. This is a quarter, and you can divide that one by 3 at least. So let's see, 12 divided by 3 is 4. 51 divided by 3 is 51 divided by 3 is 17. These cancel out, so it looks worse than it was. So the probability of taking a deck of cards, randomly picking 2 cards, if the first card is a spade, what's the probability of picking 2 spades, basically? And it's not just 13 out of 52 divided by 13 out of 52. That would be the case if you put the card back in. But because we're not putting the card back in, you have this conditional probability. So the second one says, what's the probability of getting a club the second time given that you've chosen a diamond the first time? Well, the probability of picking a diamond is 13 out of 52. So that's the probability of event A happening. The probability of picking a club second, well, by picking a diamond, I don't reduce the number of diamonds. So I still have 13 cards, 13 diamonds, or 13 clubs in the deck, but I have one less card in the deck. So in this case, because it's 2 spades, I decrease both the numerator and the denominator. The denominator because I take a card, the numerator because I take a spade. Here, I decrease the denominator by 1 because I've taken a card, but I don't decrease the numerator because I haven't taken a diamond. I haven't taken a club. So in that case, if I wanted, what's the probability of me picking a diamond first and a club second, I would multiply these two together. Okay, so let's see if you guys can figure this one out. So what's the probability of, in this case, it's not given this, given that, it's basically, it says 2 face cards. So the way to look at that is, what's the probability of getting a face card given there's really 2 parts to this. What's the probability of picking a face card given a face card first? Okay, so that's the conditional probability question. So try to figure out what that is based on what we did before. To actually answer the question, what's the probability of getting a face card and a face card? So it's 2 parts. There, you're going to have what's the probability of getting a face card the first time, and then the probability of getting a face card the second time, given that I got a probability that I chose a face card the first time. So let's see if you can get both of those questions answered. So this first question is, what's that? So we'll ask you guys a question. We'll ask you the final answer. So Austin, if you have a 52 card deck, what's the probability of getting a face card? How many face cards are in a deck of cards? 12. And how many cards are in a deck of cards? 52. So the probability is going to be, it's going to be what? 12 out of 52, right? Yeah. So the probability, this probability here is going to be 12 over 52. That's how many face cards there are in a deck. Now we have to answer the second card question. So, Adriana, I'm going to ask you, so if you've chosen a face card, how many face cards are left in the deck? 11. So that's going to be the numerator. And how many cards are left in the deck? 51. So that product will give you, that gives you the probability. The product of those two give you the probability of getting 2 face cards. Now for no face cards, it's the, you might think, oh, well, is that going to be 1 minus the probability of getting 2 face cards? And that's not true, because you can get 1 face card the first time, you get a face card the second time. What you would do here is you'd say, well, how many cards in the deck is not a face card? Well, it's going to be 40, because there's 12 that are face cards, therefore there are 40 that are not face cards. So you'd have 40 out of 52, and if the first one you choose is not a face card, then how many are left to choose from that are not face cards? Well, there are going to be 12 face cards and 39 not face cards, and they're going to be 51 cards. Okay, let's look at this one. The first card is a jack. So we figure out what the probability, this is the probability of picking a jack, is going to be 4 out of 52. So that's probability of event A happening. Now, a jack is a face card. So if the, oh, it says both are jacks. Okay. So if the first card is a jack, there's probability of picking a jack out of a full deck of cards is 4 out of 52. Oh, this does say face card. I don't know why it gets, okay. And the second card is a face card, but the jack is a face card. So instead of 12 face cards remaining, because the first chosen was a jack, there are 11 face cards remaining, and there are 51 cards. And so you multiply those together. Okay, I'm going to go ahead and assign the homework for this section. I'm going to come back. We're going to, you know, we have time to do a few more problems. Actually, what we'll talk about is the one that's the problem that I show there. We'll come back and finish the other ones next time. But there's this interesting problem of, you know, what is the probability given a number of people that at least 2 of them have the same birthday, meaning the same, not the same year, but the same month and the same day. So mine's January 11th. You know, what's the probability of somebody else in this class having the same birthday as mine? And you might think, pardon me? Twins, yeah. If you have twins in your classroom, that makes a big difference. Assuming no twins in your classroom. Yeah, so the way you do it is you do it in a multi-step process. So it's not just 2 steps. It's however many steps the people are in the class. So what you ask, the way you solve this problem is you say, you know, what's the probability of the next, so, you know, with me, I've said what my birthday is. What's the probability of people in the class not having the same birthday? So it's one of those complement problems. No. Well, then that's different problems. we can think about it. Let's not worry about leap years. Don't make it more complicated. So the probability that you don't have the same birthday as me is, well, there are 364 days remaining in the year. So the probability of the next person I choose of not having the same birthday is 364 over 365. Then the next person that I choose, the probability of them not having the same birthday as the previous 2 is there's, you take 363 out of Is it 365 still or not? Or is it 360? I can't remember whether it's 365 or 364. Let me think. It must be 365. Yeah, otherwise it just cancels out. So every time you add a person onto this, the numerator is going to be reduced by 1. And you're having this cumulative probability of that I don't have the same birthday, and you 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 don't have the same birthday. So it is a conditional probability as I go along. So I have a spreadsheet that shows this, how it works. So let me open up this and see if I can find it. I guess that wasn't it. Let's go to maybe it's in chapter 11. Oh, there it is, birthday problem. That doesn't look like the birthday problem. I don't know what that is. Somebody else. Maybe I got rid of the birthday problem thing. Let's go to section 3. See if it's in there. Nope, not there. And yeah, I don't know what that all's about. I will generate it now, so let me share it. I thought I had it, but I didn't. So what we're going to do is we're just going to have a column that has the number of people in our classroom. And then what you do is you calculate the probability of B given A kind of thing. I'll use that as my, and then we have the product of each step. So the way it works is these are how many people in my class, and each time, each step, the probability of the, so what I'm going to do is I'm going to start with 365 minus this number. I'm going to divide by 365. And apparently I did something wrong here. Let's look at this. I divide by 365. That seems too big. Oh, it's A2. Yes. Let's fix that. Okay. So that's the probability of two people that I pick in a row having the same, not having the same birthday. You can copy that down. So you copy that formula down all the way to the bottom. And to get the cumulative probability, what you do is you take the original probability, which is this one, and you multiply that times the probability in the next step of the process. And if I copy that equation down, all the way down here, and then I take this number and I subtract 1 from it because it's a complement kind of thing. So this is the probability that two people will have the same birthday. So the third column is the probability that people will not have the same birthday. So if you take 1 minus that, that's the probability that two people will have the same birthday. So the closer to 1 you are, the more likely you are to have two people having the same birthday. And let me go ahead and format this so it's percent instead of, so we'll make it percent instead of a decimal. So if you have two people, the probability that two people in this class, the first two people I choose, the probability of them having the same birthday is 0.27%. That's 1 out of 365 basically. But as you go and add more people, you'll see the probability increases. So with a class size of 10, it's a probability of about 14% that two people will have the same birthday. Pardon me? So a class of 30, you would have almost a 3 out of 4 chance that two people have the same, at least two people have the same birthday. Pardon? What's that? Oh, it wasn't enough, so it didn't work. Yeah. So if you have if you're taking biology, which has 50 people in it maybe, there's a 98% chance that two people in that class of 50 will have the same birthday. And if you get up to 100 people, well, you can see 75 people, it's a 99.98% chance that two people in that room will have the same birthday. Even though there's 75 out of 365 days, it doesn't seem like it's going to work that way. But it's this cumulative effect of each time you add somebody, the probability of the next person not having the same birthday is lower, and you multiply all those probabilities together, and so it ends up giving you some result that you would not have expected. So you have to have at least 70 people in your class to be almost guaranteed. If you have 100 people, you know, it's almost 100%, not exactly 100% probability, but it's pretty darn close. So, okay, so that's it for today.